Hi everyone, my name is Mallesh. I am a PhD student in computer science at Stony Brook University. Today, I'm going to talk about our research work that is based on 360-degree video streaming. 360-degree video streaming is central to many applications such as VR and AR. It provides immersive experience by projecting the video content in a virtual environment around the user. Because of this immersive experience, there is a significant interest from various stakeholders, ranging from users to content providers such as YouTube, Netflix, Facebook, and beyond. It's been predicted to be $1 billion business in the near future. And because of this immersive experience, the popularity of 360-degree video is also on the rise. But the grand challenge with the 360-degree videos is that they require 8 times more bandwidth compared to regular videos for the same quality. To illustrate with an example, here is a panoramic scene that is extracted from one of the 360-degree videos. Here the downloads this entire panoramic scene and renders only the small portion that is shown in this red rectangle in the virtual environment that is based on the user's direction of view. What this means is that despite the fact that the user needs this small portion of the scene that is shown in this red rectangle, the client downloads this entire panoramic scene, which requires much more bandwidth compared to what the client actually needs. So there is a significant bandwidth waste here. To avoid these bandwidth problems, current solutions take a viewport adaptive streaming approach. The basic idea in viewport adaptive streaming is that a video is divided spatially into tiles. A tile here means a block of pixels. For example, here 192 by 192 pixels. After dividing this video into the spatial tiles, each of these tiles are encoded independently and stored on the video server. Now that the tiles are independent, the client on the client side, the client can employ some sort of prediction mechanism to predict the user's direction of view and fetch only the tiles that are specific to the user's direction of view. And by using this technique, the client does not have to download the unnecessary parts and hence can save the bandwidth significantly. But the problem with this viewport adaptation technique is that the prediction. As you can imagine, predicting a user's head movements in general is extremely challenging, even if you use enormous amount of data. For example, the figure on the right side shows prediction accuracy on the y-axis with different prediction windows into the future. The plot shows that the prediction accuracy drops significantly as we try to predict even 1, 2, 3, 4, even in terms of 3 seconds. What this means is that if we mispredict where the user is looking at, the user will end up having tile misses and can have bad experience. To accommodate this, to compensate this kind of tile misses, the state-of-the-art solutions, the current solutions, use some sort of heuristics to fetch more and more tiles to avoid these tile misses. But fetching more tiles means more bandwidth requirement and overall reduction in the video quality because of the adaptation techniques. And another fundamental problem with these current solutions is that they are completely network-centric. What that means is that the network is the fundamental bottleneck in these solutions, where a slight change in the network can directly influence the user's video quality. In this work, we want to explore some other means of improving this client's video quality outside of these network-centric solutions. One such solution, one such opportunity that we find here is a concept called super resolution. The key idea behind super resolution is that it takes a low resolution image or video and tries to add some details to produce a high resolution content. Although the idea is kind of old and goes back to the 90s, this is getting more and more attention because of the recent computer vision techniques based on deep neural networks, or the DNNs. But the problem here is that DNNs are computationally expensive and and it has not been used on mobile devices ever. But we also have another opportunity in terms of computation or the computing power. Over the decade, we have seen a tremendous increase in the computing power. For example, the figure on the right side shows that since 2009, we have seen a tremendous growth in terms of teraflops in GPU computing capacity. And interestingly, all this computing capacity is often underutilized while watching a video because of the dedicated hardware video processors. So what we can do is we can leverage this underutilized compute capacity to run this super resolution model on mobile devices to enhance the video quality on the client side, thereby reducing the burden on the network. But the key question here is to ask, is this compute power enough to do this super resolution? Is this compute power enough to run this super resolution on high resolution content such as 4K and 8K? This brings several challenges on DNN-based super resolution, especially because the DNN models are bulky and slow and have slow inference and produce larger model sizes. The model size is also important here because it competes with the actual video segment download. So to understand these implications, we train a super resolution model for 1 minute duration and see the performance in terms of inference rate and model size for different resolutions. As you can see, the inference rate, which is calculated in terms of the frames per second that are inferred using the super resolution model, goes almost less than 2 frames per second when it crosses 4K resolution content. And also the model size increases significantly as we increase the resolution. Another fundamental problem that we face with super resolution is that there is a significant variance in the quality enhancement. That is, when we pass a frame or an image to the super resolution model, the quality of the output frame is highly varied. For example, the figure on the right side shows that the quality can vary anywhere from 28 dB to 40 dB. So it is unclear which frame to send to super resolution for quality enhancement and not which frame not to send. So keeping these challenges in mind, we ask these questions. How do we make these models smaller and faster inference and have faster inference while having the better quality? To answer these questions, here comes our first contribution in our work. We present lightweight micro models for super resolution. More specifically, we build these micro models by training a model for each segment as opposed to training a universal model, a universal bulky model based on a large video or a large corpus of videos. To give one example, let's say we have this 360-degree video segment. We tile this segment as usual, and we have these independent high-resolution tiles. So we take these independent high-resolution tiles and downscale significantly and further compress using the traditional compression algorithms. And we call these tiles as ultra-low resolution tiles. We input these ultra-low resolution tiles to the super resolution DNN model and the high-resolution tiles as the ground truth. And we try to reconstruct these high-resolution tiles from the ULR tiles using this DNN-based super resolution model. So once the model is trained, the client can fetch this model along with the actual segment download. Once the model is downloaded onto the client can generate these. The client can generate only the viewport specific tiles. The client can enhance only the viewport specific tiles as opposed to enhancing the quality of the entire panoramic scene. So by having these lightweight micro models, the key benefits that we have are we have this smaller model footprint because we are training on only shorter segment. And because the model is extremely small, the inference is also kind of faster now. But at the same time, we also face additional challenges. Even with these micro models, even with the faster inference, we are able to achieve only few tiles per second. For example, this figure shows that that inference rate on y-axis in terms of tiles per second, and for different tile sizes on the x-axis on different GPUs. The maximum number of tiles that you can generate are below 15. So in general, if a viewport has more than 15 tiles, then we have to select a subset of the tiles to enhance the quality. So this raises number of questions. For example, which tiles to download at what resolution from the server, and which tiles to generate using super resolution, because we can only generate a few tiles per second, and which tiles to ignore because we don't need any tiles that are outside of the viewport. So traditionally, an ABR algorithm should be able to take care of these, should be able to answer these questions, but all of the current ABR algorithms are focused on only network as a resource. They do not take compute as a resource. So here we need a new ABR algorithm that combines compute and network resources and optimally answers these questions. So to do that, we propose our second contribution here, neural aware ABR algorithm. What this does is it optimally combines the compute and network resources and answers the aforementioned questions. To give you a high-level idea, so here is how our neural aware ABR algorithm works. So the server has these different tiles in different qualities, and along with this, we have our ULR tiles as well. And our client, typically it requests these tiles, and video server responds the requested tiles. And in a typical video adaptive streaming system, we provide these tile probabilities. In our work, we use off-the-shelf video viewport prediction techniques to input these tile probabilities. Once we give this input tile probabilities, the client player takes the compute and network capacity and selects different tile qualities and asks the server for different tile qualities. And for the rest of the tiles, the server sends the ultra low resolution content. Once the client receives these tiles, it sends the high resolution tiles in the player buffer for the further playback, while sending the ultra low resolution content or the low resolution content to the GPU for further quality enhancement using the super resolution model. Once the tiles are enhanced, tile qualities are enhanced, they are put back to the player buffer for further playback. So effectively, we achieve this overall high quality by using the combination of this network capacity and this new compute capacity. So the way we achieve this overall high average quality is by modeling this compute and network capacity using the several quality of experience metrics. For example, we have the expected average expected quality, which is a combination of the downloaded tiles as well as the generated tiles using the super resolution. And we also have this tile miss ratio in case of the very inaccurate viewport prediction measurement. And we also incorporate the quality switches spatially and temporally. So overall, the quality of experience looks like a combination of these QoE performance metrics. So we formulate an ILP problem to maximize this QoE, and we try to find a fast solution by using the greedy algorithm. You can find more details of this algorithm and the ILP formulation in our paper. So putting everything together, our parsec system looks like this. We have this offline super resolution model training, and then we have the ultra low resolution tiles and micro models along with the traditional H.264 or HEVC encoded segments. On the client side, we have our neural aware ABR algorithm that selects different bit rates based on the network capacity and schedules different tiles for inference on the GPU. The neural aware ABR algorithm takes the tile probabilities from the viewport prediction and network capacity and compute capacity, as well as the generated tile quality as an input to make these decisions. With that, we proceed for the implementation and evaluation of our parsec system. We implement a parsec on a Pixel 3 phone using GPAP framework, and our server is hosted using a Linux server using Node.js server. We train the super resolution model, the DNN-based super resolution model, using Keras as a TensorFlow backend. We evaluate parsec with other algorithms over diverse network conditions on a 360-degree video dataset that was released in MMSIS 2017. We compare parsec's performance with different algorithms. The first algorithm is VP only, which downloads only the viewport specific tiles by using the prediction technique. We also compare with Flare, which downloads additional tiles around the predicted viewport to avoid the frequent tile misses. We also compare NAS, a state-of-the-art regular video streaming system that uses super resolution to enhance the video quality on the client side. We also, for a fair comparison, we also modify this NAS regular for 360-degree video and show the performance comparison with parsec. We compare average quality and tile misses first, and compare performance of parsec with other algorithms. As you can see, the quality level is given on the x-axis and the CDF on the y-axis. Here, the green curve shows our parsec. As you can see, the performance is significantly improved compared to the next best solution available, which is Flare. We see about 30% improvement in terms of the average quality level. And similarly, we observe 26% improvement at the 90th percentile in terms of tile miss ratio. So the key benefits are coming here from the super resolution as well as our neural aware APR algorithm that makes use of both compute and network resources as opposed to the state-of-the-art solutions, which use only network-centric solutions. Here, it also performs better than NAS because NAS was originally designed for the regular videos as opposed to 360-degree videos. We also have the overall QoE performance. Again, the green curve here represents our parsec system performance, which shows 37% improvement compared to the next best solution, Flare. We also want to emphasize the fact that parsec has a significant benefit as we increase the computation for computing power. For example, as you see, the whiter ones are desktop grade GPUs and the darker ones are mobile grade GPUs. As we increase the compute capacity, the performance metrics improve significantly. So in conclusion, we present parsec, a panoramic video streaming system that is based on a DNN-based super resolution. And we also present a neural-aware ABR algorithm that takes compute and network resources and optimally selects bitrate decisions. Finally, we also presented that parsec provides high quality of experience compared to the state-of-the-art solutions. For more details, please visit our website and reach out to me through the email. Thank you.